Hello, I'm Vivek Sarkar from Georgia Tech, and my co-authors and I would like to welcome you to this presentation of our paper on the Intrepid programming model for data science application kernels. Our work is motivated by the fact that there are two exciting and major disruptions underway in our computing stack. One is from the bottom up. As we approach the end of Moore's law, we see that we are exploring an era of extreme heterogeneity where memory units, compute units, instruction sets are all getting more heterogeneous. And the other is from the top down, where we recently have a exciting proliferation of new applications related to data science and machine learning, and they have their own algorithms and their preferred libraries, frameworks, and programming models. So what we are interested in is fulfilling this need for programming systems that can bridge between these two disruptions. When we look at current approaches for programming systems for data science applications, one very common approach is to use a high productivity language that is accessible to data scientists, such as Python or Julia, and augment it with high performance libraries that can take advantage of the underlying hardware. So for example, you may have libraries such as NumPy, SciPy, and CuPy. The main challenge with this approach is that the library APIs may not adapt to the needs of these new applications as new algorithms are being developed. On the other hand, we have domain-specific languages that support very targeted domains and have the capability of generating highly optimized codes for those domains. Some examples are multiple DSLs for machine learning, including TensorFlow, the Halide DSL for image processing. But the challenge here is a data scientist, when putting together an end-to-end application, is going to need more than one DSL, and they're also going to need a base language like Python or Julia as the underlying high productivity language. So the motivation for our work is to combine the benefits of high productivity languages and domain-specific languages with the Intrepid programming model and an approach that we refer to as discipline-aware languages for data science. So many of you have seen this triangle before between performance, productivity, and generality. And the key point of domain-specific languages is that they're furthest away from generality, but leverage and offer the best they can with productivity and performance with that trade-off. We would like to expand this frontier back and pull it a little closer to the generality end of the triangle by making sure that we can encompass all domains related to data science. So our Intrepid programming system delivers performance, productivity, and portability. It is based on a Python syntax to make it easily accessible to data scientists. It does simplify programming for heterogeneous hardware and post-Moore hardware. And even though it is based on Python, it differs from Python in a few significant ways. One is that it's designed to be a language for writing kernels, that is, Intrepid functions that can be mapped onto computational kernels, not the entire application. For that, we'll appeal to all the rich functionality that's already available in Python for the main program and the surrounding code. The second is that it is designed for ahead-of-time compilation with high-level compiler optimizations and C++ code generation. You will see an example of coding in Intrepid very soon, but I'd like to give you a brief summary of the Intrepid language. It contains data types, statements, operators, and library functions that should be easily recognizable by any Python programmer. We do have an extension to statements related to parallel statements that include parallel for loops, task creation, task termination, and mutual exclusion. We also have this constraint that all functions must include type declarations for parameters and return values, and we use that for type inference so that we can, in a ahead of time compilation, infer types for all the local variables in a function.
Let's start by seeing how Intrepid looks to a programmer who already knows the traditional Python data analysis stack. Here's a real Python code fragment, not written by us. It comes from one of the DARPA machine learning benchmarks and is called Sinkhorn WMD. It involves both dense and sparse matrix objects. Through operator overloading, the libraries that operate on these objects allow the code to closely resemble the mathematical notation you would see in the pencil and paper algorithm. For Intrepid, one key goal is to provide an incremental path to performance through lightweight annotations and targeted abstractions. So for instance, here we add dense matrix type annotations. These use standard Python syntax with Intrepid-specific multidimensional array types. Intrepid also implements a sparse matrix API. That includes a type annotation shown in lines 3 and 4, as well as a constructor in line 6. The design of the Intrepid API tries to preserve what today's Python programmer expects. There are a few small changes which allow our compiler to do high-level performance optimization. Nevertheless, we hope you'd agree that the annotation burden is small. Indeed, as part of our ongoing work, we're refining the API and extending the compilation system to reduce that burden even more. So here's an example of what you might write in a future version of Intrepid. As a point of comparison, here's what the same kernel looks like in Julia. That's another popular language for numerical computing. So the style and syntactic weight of programming in Intrepid and Julia are roughly the same. So a natural next question might be, how does the performance among the Julia, Python, and Intrepid versions compare?
To answer that question, we undertook a detailed performance evaluation using a benchmark suite comprised of several Python-based data analytics applications. Our benchmark suite is a mix of library call dominant and non-library call dominant applications to showcase Intrepid's performance across the spectrum. Our test bed is a modern server machine comprised of a dual-socket Intel CPU and 192 gigabytes of main memory. Each benchmark reported here is run 11 times, and the average of latter 10 runs is reported. The standard deviation between runs was found to be between 0.06% and 3.6% for all benchmarks. Our baseline is idiomatic Python running version 3.7.6. First, let's look at Intrepid's performance when compared against Cython, Numba, and baseline Python. On the y-axis here, we have the performance improvement factor over baseline Python, and on the x-axis, we have the various benchmark programs we ran. As far as single core performance goes, Intrepid offers at least an order of magnitude improvement over baseline Python for all applications that are not heavily reliant on library code. The exception here is ISTA, for which Intrepid shows 1.5x performance improvement. Since ISTA is heavily NumPy reliant and the focus of this work is to improve native Python code, we do not observe a significant speedup. On average, Intrepid offers 20.07x speedup when computed using harmonic mean over baseline Python. Moreover, Intrepid does not suffer from performance loss that is observed for some applications when run using Cython or Numba. Next, let's see how Intrepid performs when compared against Julia. Here, on the y-axis, we have speed up over baseline Python, and on the x-axis, we have benchmark programs. The first three benchmark programs come from Julia's micro-benchmark suite and are small programs with a few lines of code. Here, Intrepid offers either similar or better performance than Julia. The last benchmark program on this plot is Sinkhorn WMD, the code for which we showed you earlier. Here, Intrepid offers 88.5x performance improvement over the Julia version. is going to be attributed to our high-level optimizations. My colleague will now talk about our toolchain and these optimizations.
Now we show how an Intrepid program is compiled and executed eventually in our pipeline. In the first step, the Intrepid source code is compiled to C++ code by our compiler. This slide shows an example Intrepid source code and also the generated C++ code for that. So in the C++ code, there is this pydd shape function. That is a library function that returns the shape of a given array. So Intrepid arrays can also work with NumPy arrays without copying the data in the C++ code. After going through the front end, we perform a number of high-level optimizations, which we will get into in the next slide. And after generating the C++ code, we can either compile it to a normal object code, or we can hand it to a Python C module compiler, which compiles it to a Python C module that can be used in Python code. Now I'd like to talk about a number of optimizations performed at the AST level and how they contribute to the performance improvement. The first optimization is looping variant code motion, which is a classic compiler optimization. Besides scalar variable assignments, in our case, we also need to consider assignments to array references and array elements. The second optimization is dense array operator fusion, which can improve data locality. The next optimization focuses on sparse array operations and tries to eliminate redundant computations for the zero elements in sparse arrays. Finally, the last optimization tries to reduce redundant memory allocations and recycle memory spaces. This table shows how much each optimization improves performance for each benchmark. Basically, it shows that all optimizations are important and no one is superior to all others, and also no optimization cause degradation for any benchmark. And the paper has more details for the optimizations.
I would now like to summarize what you've heard so far. You've learned about the Intrepid programming model and how it is based on Python semantics that is appropriate for data scientists. You got an under-the-hood look at our compiler and its ahead-of-time toolchain and the high-level optimizations that it performs, especially for computations that occur in data science applications. Intrepid also supports high portability, and with its generation of C++ code, the paper includes details on how it can be used to map to post-more accelerators and architectures. We also shared some very exciting performance improvements relative to base Python when using Intrepid. We saw that for these data science benchmarks, we could get 1 to 3 orders of performance improvement just in single core execution time. These are for general applications where the performance is not dominated by native libraries. For one application where the performance is dominated by a native library, the improvement was modest, but it was still a factor of 1.5. Now, in the spirit of the Onward conference, we did not want to just stop after sending in the paper. This is very much work in progress. We have been working on extensions that enable Intrepid to map onto distributed heterogeneous runtime frameworks, as well as we've been working on completing the implementation for the parallel statements, async, finish, isolated, and also completing the support for targeting post-more accelerators. I would just like to share with you some late-breaking news, which is that our extension for distributed heterogeneous computing has been completed. We have our first prototype. What we've done is we've added a pass to the Intrepid toolchain that generates Python code after high-level optimizations. And this enables us actually to generate code that maps onto the Ray runtime that can distribute Python tasks onto CPUs, GPUs, FPGAs, and across multiple nodes in a cluster. Here's one example that we've been able to demonstrate. This is from signal processing. It's called space-time adaptive processing. And what the toolchain is able to do is take the code in the red rectangle on the left and split it into tasks that are pure functions, spawn them, as you can see in line 15 on the right, and then wait for the tasks using futures in line 18 on the right. And the initial results are very, very encouraging. We've been able to take a code that was written for CPUs with NumPy and convert it to code that uses CuPy to just get 2 orders of magnitude performance improvement with the GPU, and to spread this computation across multiple GPUs on multiple nodes, something that can be very, very challenging for Python programmers to do today. So we are excited by this work that's underway with the Intrepid programming system and look forward to sharing more results on our ongoing progress with you in the future. We would very much welcome your input and your feedback and your comments. And thank you so much for listening to our presentation.